Hello everyone, thanks for coming to this section. My name is TingTing. I'm from the University of Delaware. Today I will talk about the prediction of consolidated cohesive bottom erosion by wave action. First, the motivation. A consolidated cohesive sediment layer exists below the sand layer on some beaches along the Great Lake and the Gulf of Mexico. Look at the left photo. In the Lake Michigan, the bottom is cohesive sediments. The cohesive sediment contains sand. Sand is released from the bottom after a long time sand transports offshore, and the cohesive bottom comes up. It may become like the photo. Beaches in the Jefferson County, Texas. Unlike sandy shore, once the cohesive shore was eroded, it cannot recover. But it's said that a sufficient thickness of sand layer can protect the underlying cohesive bottom. Our understanding predictive capability of cohesive sediment shore erosion are rudimentary, probably because of no prototype scale data with detailed measurements. Sand and clay interaction model. This figure is most clearly to illustrate our formula and the parameters. Look at the coordinate x is positive onshore with x equals 0 at the seawater boundary. J is positive upward with 0 at the still seawater level. And the CB is sand surface elevation. CP is clay surface elevation. This clay pair simply expresses the cohesive sediments which contain sand and clay mixture. When this clay pair is eroded, the sand will release from the eroded pair. The released sand may move onshore and offshore by wave action, as well as deposit above the clay bottom. The sand layer thickness HP is defined as the vertical distance between the sand and the clay surface elevation. CB minus ZP, the clay erosion depth E is the vertical variation of the ZP with time. In the model, we assume the eroded clay all transport offshore and didn't settle again, so E is positive or 0 because of no recovery of eroded clay. Conservation equation of sand volume is shown here. The left part, this part, indicates sand release from the eroded clay bottom per unit time. The released sand can transport onshore and offshore via the bedload and the suspended load, or deposit above the clay surface to form a sand layer thickness. The deck erosion model was developed by the Kobayashi and Wisner 2015 and incorporated in the seashore model by Kobayashi 2016. It is used to predict cohesive bottom erosion depth E. The function is adjusted here. Abrasion and the protection function was added here. F, when F is equal to 1, it is the case of the snow sand for the deck erosion model in 2015. The product of the full density, clay resistant parameter, erosion rate are related to the wave energy dissipation rate. In our cases, we need to consider the sand motion, the effects of sand motion above the clay surface. So there are two statements. Canvas presents that a single layer of sand particles increase till erosion, and however, a sand layer of 1 centimeter or more prevented till erosion in lab experiment by Scaffi and Bishop. These abrasive and protective effects of sand particles on the clay bottom are included in the equation 5 for the function f. We can see this figure to understand this new function f. It shows f as a function of normalized sand layer thickness h star. When sand layer thickness is small, f is larger than 1, resulting in more erosion. It serves as the abrasive effect. And then as the sand layer thickness is increasing, f approaching to 0, the erosion rate is approached to 0 too. So it serves as the protective effect. The numerical model will compare with the available data in the lab experiment by Bishop and Scaffi. They did field work to in the lake area set to collect the entire teal samples. Because it's hard to make the artificial teal, the teal consists of 21% sand and gravel, 33% silt, and 46% clay. The values of the 21% will be used as the sand volume fraction FC as input to seashore. Then they use the entire sand teal sample in the lab experiment. So this figure shows the test setup in the blue. The collected teal samples were put in the middle part, dark part, and the silver and the gray planes are fixed planes. The initial profile was built as an equilibrium beach profile. SCAF in 1995 reported erosion rates and hydrodynamic data for two tests in water depths of 75 and 85 centimeters. We named them as S75 and S85. The reported data include the teal profile elevation, wave-height, peak period, and the water depths for input, and the hydrodynamics data smooth the erosion rates for output comparison. The test duration and the sand layer thickness are not reported. The unknown sand layer thickness is P, partly because difficulty in measuring the thickness less than 1 millimeter. So initially we assume the no sand layer above the clay bottom, so sand and the clay surface elevation are the same. Thus, we see the initial bottom profile for S75 and the S85 tests. The reported erosion rate data is only available in the middle part. The clay resistance parameter assay in this part is calibrated at 30, and the sand volume fraction FC is 0.21. For these two parts with all the erosion rate data, the left RC is 1000 because it's a stiff, and the FC is 0 because it's a fixed plane. The computation is for 10 hours with break ratio parameter gamma equal to 0.6 and 0.7. The computed hydrodynamic changed little during the 1 to 10 hours because very small erosion. Next figure will show the effects of the computed hydrodynamics using gamma equal to 0.6 and 0.7, comparing with the measured data. The first is significant wave height. The up panel is the S75 test and the lower panel is S85 test. The duration is 1 hour. The circles are measured wave height data, and the solid line is the computed result using gamma equal to 0.6. And the dashed line is gamma equal to 0.7. The agreement looks good. Then is fraction Q of broken waves. The measured value Q, the circle points, were obtained by counting the number of broken and unbroken waves, but the criteria was not stated. The velocity standard elevation measured data are close to the computed result with gamma equal to 0.6. However, the measured velocity was collected at 4 centimeters above the teal surface, while seashore computes and outputs the depth averaged velocity. Overview of these three figures. The increase of gamma from the 0.6 to 0.7 that delays the wave height decay and the wave breaking, resulting in the increase of the cross-shore velocity. Here is PBHPF and the erosion rate. Well, here we only shows S75 test with gamma equal to 0.7. The sand movement probability PB doesn't change too much with time. The red line is computed result at 1 hour, and the blue line is the computed results at 10 hours. And the measured erosion rate are dark line here. So, and then we see the sand layer thickness HP is increasing with time, indicating clay bottom continue erosion, and the sand gradually released from the clay bottom. The function f is corresponding to the HP. As HP increase, the function f decrease. For this panel, the computed erosion rate is larger at 1 hour, and the computed 10-hour average data is close to the measured data. Rapid decrease of the computed erosion rate from the 1 hour to 10 hour may be because the released sand accumulated above the clay bottom, and the thickness is increased to protect the underlying clay bottom. Two applications were performed to show the long-term process. Both applications, the duration was increased to 100 hours. The initial profile, water level, and the water conditions did not change, but the fixed zones at the landward and the seawall edges, these two parts are artificial. This may affect the long-term profile evolution, so we'll use the RC equal to 30 and the FC equal to 0.21 for the intel profile. And here show the layer profile evolutions. The dark line is the initial profile, and blue-red line are sand and clay surface elevation at 100 hours. The maximum erosion depth and the deposit sand height are less than 6 cm and 0.5 cm. Most sand released from the eroded clay deposited near the shoreline. This figure is still showing the small changes. So for the second application, we divide the hypothetical protocol test S75P and S85P to examine the scale effect in these two tests. The protocol tests are based on the fluid similitude with the loss ratio of 1/4. So the wave height increased to 1.04 meter, and the time, the corresponding time ratio is 1/2. So the peak period TP is 6.2 seconds, and the duration is 200 hours. The same tier is used because no similitude exists for cohesive sediment erosion. Here shows the video of the profile evolution. Time is from 0 hour to 200 hours, and here is the length. So let's see the video. So within 30 hours, the erosion occurs very fast. And then sand transport the onshore and offshore to get a stable states. The sand layer thickness is about 0.1 meter at 200 hours, which can protect the eroded clay surface. And for here, the erosion rate, we can have a better explanation. The blue line is 20-hour average, and the red and the green line are the 100-hour average and the 200-hour average erosion rate. The first 20-hour average, the erosion rate is very large, indicating the cohesive sediment is eroding fast at the first, and then the erosion rate slowly approach to 0 during the 100 to 200 hour, indicating the thicker sand layer can protect the clay bottom, and the erosion will reduce and stop. The conclusion. CIRO was extended to incorporate the basic process of cohesive sediment and the cohesionless sediment interaction, mixed clay and the sand bottom, and the irregular breaking wave. It was compared with TIL erosion test. The agreement was reasonable, but the erosion rate comparison was uncertain, partly because of no sand layer thickness data. Longer duration computation indicate a decrease of the clay erosion rate resulting from the deposition of sand release from the eroded TIL. Thank you. Any question?